Molecular polarity is important for understanding how many chemicals interact. Formaldehyde is a small molecule. It's neutral, has no overall charge. But within that molecule, there's a distortion of the electron density. And there's a greater electron density around the oxygen atom there on top, which has a partial negative charge. And there's less electron density around the carbons and hydrogens at the bottom of the molecule is shown, giving it a partial positive charge. By separating the charge in the molecule, these molecules, if they orient appropriately, can be fairly strongly attracted to one another. They can also dissolve or interact well with ions and other polar molecules, and these properties and their effects on solubility are going to be really important as you go forward in chemistry. To predict whether a molecule will be polar, we need to look at two things. First, it must have one or more bond dipoles. So we're going to use electronegativity to determine if there is a polar covalent bond. If there are no polar bonds, we're not going to see molecular polarity. And if it has those polar bonds, then the molecule has to have a shape that allows the bond dipoles within the molecule to add together to give a net dipole moment, or that overall separation of charge in the molecule. We're going to look at a bunch of examples here to sort of talk this through. And my first two examples here are molecules that have a single polar bond. And anytime there is a single polar bond, the overall molecule will be polar. So it meets the first criteria of having a polar bond. The electronegativity difference in both of these cases is greater than 0.4. And with that polar bonds, the second step was to look at shape to see if it adds together to give a net dipole moment. And the problem there is that on occasion, if you have two dipole moments in a molecule, they might cancel out. When there's only one, it can't. So both of these examples are polar. Okay, here's an example looking at molecules each with two polar bonds. So carbon dioxide in the top will be nonpolar. It meets our first criteria of having polar bonds, but when we take these two bond dipoles in a linear molecule like carbon dioxide, one travels to the left, and if we add the second one, we put it head to tail, it ends up going right back to the starting point, and there's no overall bond dipole. The second example of water is very polar. And the key thing to realize here is that it is not a linear molecule. Water is a bent molecular shape due to the two lone pairs there on the top. It has a tetrahedral electron geometry, and there's a bond angle in here of about 109.5 degrees. Now, both of these bonds are polar and pointing towards the oxygen. But when I take these two bonds, one pointing up this way and the other coming this way, when I add the two vectors together by putting them head to tail like that, there is an overall molecular dipole. And that dipole runs sort of from between the hydrogens up through the oxygens towards the lone pairs. The oxygen lone pairs have partial negative charges, and the hydrogens will have that partial positive charge. And this becomes important. Water is very good at dissolving salts and ions, and it's because it can position or arrange the water molecules to favor the attraction between the ions and one end of the water molecule. Okay, if we look at things with three polar bonds, boron trichloride here in the top. Note that boron does not have an octet. It is one of two atoms that routinely forms compounds with fewer than 8 electrons assigned to that central atom. Beryllium tends to form just 2 bonds. In this case, boron trichloride will end up being nonpolar, even though it has 3 polar bonds. And in this case, it's a trigonal planar structure. There's 3 electron groups around it. And if we add those three arrows in the trigonal planar structure, they're separated by about 120 degrees. It will sort of come like this and then come back down and come right back to the starting point. Those three bond dipoles will add together to give no molecular dipole, therefore nonpolar. In contrast, phosphorus trichloride will be polar. It still has three bonded atoms, but it also has this lone pair of electrons on the phosphorus, and this makes it a tetrahedral electron geometry and a trigonal pyramidal molecular geometry. So I'm going to draw it a little differently. I'm going to sort of rotate it. I'm going to have the phosphorus, and then up above the phosphorus I'll have the lone pair, and that lone pair would be sort of in the plane of the page up there. There'll be a chloride coming down and to the left, again in the plane of the page. And then the other two chlorines, the wedge representing a chlorine coming out of the page towards you, and then the dashed line representing one going back into the page. The angle between all of these is about 109.5 degrees again. And they're all down a little bit. They're a little past 90 degrees below that vertical axis as I've drawn it. And so when we look at these, and we add these bond dipoles together, each pointing towards the chlorine, each one, this is going to be a little tough to draw, this is sort of coming out and then back into the page, sort of spirals down a little bit, and we're going to end up with a molecular dipole pointing away from the lone pair of electrons on the phosphorus down towards the chlorine atoms. Okay. So again, three bond dipoles, but the shape means when we add those bond dipoles, there's a net dipole moment that results. Okay, when we go to four things around the center, carbon tetrachloride is a nonpolar solvent. It has four polar bonds, and this one I'm not going to be able to draw clearly. Well, I'll try. It's a tetrahedral geometry around that carbon, so we have sort of one coming down, one coming sort of out towards us, getting a little fatter maybe, and then one going back in, and then that last one, this one here that we didn't have last time because of the lone pair, comes back up towards that original atom. And so in this case, all four bonds will add together and result in no net dipole moment. So even though there's polar bonds, the molecule is not polar. These last two are in fact one molecule. This is methylene chloride, or dichloromethane is another name for the compound. And both of these are polar solvents. Or this is a polar solvent. Both of these representations are polar. Now, in this one, it's drawn so it looks like they cancel. And in this one, it's drawn so it looks like they don't. But keep in mind, this is a tetrahedral carbon, not a square planar carbon, and that's the problem that we're dealing with here. I'm going to sort of position this with the two hydrogen atoms, the two chlorine atoms in the plane of the page. So I'm going to put one of them up, coming down to the carbon, and then another one off at an angle of 109.5. One of the hydrogens coming out of the page, and another one going into the page. Now, if you look at this from say the upper left, you would see a structure like that. Whereas if you sort of look at it from our angle, you see the two hydrogens on one side, and you see something that looks a little bit more like that. This is a matter of perspective, and keep in mind these Lewis structures, only the connectivity mattered, not the positioning. We needed to use the VSEPR to get the positioning. Now in this case, drawn this way, we have the bond polarity sort of coming up in that way and down in this way, and if we add those two together, you end up with, again, a net dipole moment. So be sure you're drawing things and thinking about them in three-dimensional shape, following VSEPR. particularly when you get to these tetrahedral carbons. But this is a polar molecule. It has a molecular dipole moment pointing from the hydrogens towards the chlorines. Okay, so quick recap. Anything without polar bonds can't be polar. That's an easy one to toss out. Anything with only one polar bond will be polar. It has the polar bond charge separation and nothing with which it will cancel. So those two I think are pretty straightforward. The third one is a little note here, is anything with the same atom in each position and no lone pairs in the central atom will almost always be nonpolar. And so we have the carbon dioxide, the central atom. There's oxygens, or both the bonded atoms, and there's no lone pairs on the carbon, nonpolar. Boron trichloride, all positions are chlorines. Okay, no lone pairs on the boron, it's nonpolar. This trigonal planar structure, all the bond dipoles cancel. And the same was true with the carbon tetrachloride. Okay, it's a little harder to visualize. If you get a little model kit, you can see it, but nonpolar. Okay. That's not true if you had 2 hydrogens and 2 chlorines, for example, but if all the atoms are the same, that will end up working. 2 things to watch out for. First, it's the VSEPR shape, not the shape you end up drawing on paper when you do your Lewis structure that matters. That was a potential hiccup when we looked at the carbon dioxide and the water. We drew the water linear, but that doesn't mean it is linear. Okay, and then the second one is, even if you don't have polar bonds as predicted by electronegativity, if you have a molecule that has formal charges, then you have charge separation in the molecule, and the molecule will be polar.